Overfitting is one of the major challenges in predictive analytics. This video is going to demonstrate what exactly overfitting is and the problems it presents through a simulation. Here we have a scenario which we have two kinds of dots. We have blue dots and red dots, and they could represent many things. Like blue dots could represent the customers that buy a product, and red dots those who don't. Blue dots could represent patients that test positive for an illness, and red dots patients who test negative. The goal here is to predict which dots are blue or red based on the values of the x or the y-axis. What you see here is the collection of dots in different periods in the future. So you could think of each time as 1 month. So this is the general distribution of the dots month by month. So we have here actually simulated data. And I'll tell you right now that there is a general pattern to it, in that in general, the blue dots tend towards the top left corner and the red dots towards the bottom right corner. But there's quite a bit of randomness, so it's not a straight pattern. But we're trying to predict which dots are blue or red. So in order to do analysis like this, we need to first collect the data that we have. And for simplicity's sake, let's say that we have 1 month of data and we collect this data. This happens to be the data that we have, and we're going to model this data to try to predict what we expect in future months. So our first model is one that creates as a decision boundary a flexible curve. The decision boundary is not a model itself, but it's once you plot the values, the line that separates the values that is created by the model. So the flexible curve is created by a very flexible advanced model that can fit data very closely. So an example might be a random forest, that if you create enough decision trees, like maybe 100, 500 trees, can create a very curved looking line that really fits the data. And it can attain up to 100% accuracy on the full data set. So what we have here is a calculation of the prediction accuracy. And we have the actual values of blue and red, and here are the predictive values, and it matches perfectly. 10 blues, actual blues predictive as blues, 10 reds predictive as red. This is 100% accuracy. Then some other decision boundaries might be simpler. It might give something like a straight line. So a simple but robust algorithm like logistic regression has a straight line that separates the data. And this data isn't cleanly separated by the straight line. And so the logistic regression, which is represented by the yellow here, or let's just say a simple algorithm, gets, when there's actual 8 blue values, it correctly predicts blue 8 times, but it predicts that it's red twice and vice versa. Actual red, twice it predicts it's blue, and twice and 8 times predicts it's red. So you can see that here the logistic regression predicted that these two should be blue, but they're actually red. So generally, any prediction above the line is a blue, and prediction below the line is a red. So that's why the logistic regression above the line, it should be a blue, but these are actually reds. And these two being below the line are predicted reds, but they're actually blues. So this is only 80% accuracy. So now in subsequent periods, let's suppose we have our model. So we have our flexible model, green, and we have our simple model, the straight line, which is yellow. These are our two models. And now in the next 5 months or next 5 time periods, let's see what the data actually turns out to be, to see how well our models have predicted the future data. So again, this is simulated data, and the way to interpret it is that once the dot appears above any line, then the prediction is that it's a blue. Once it appears below the line, the prediction is that it's a red. So here's our first prediction. There's a red, and being above the lines, well, everything that's above the line is predicted to be blue. So this is above the flexible curve, so that's wrong. Predicted it was blue, but it's actually a red. And this is above the straight line, which was predicted blue, but it's actually a red. So both of them got that first one wrong. Accuracy is 0. Okay, the second one here is a blue. So everything above the line is blue. It's predicted blue, so that one's correct for both of them. So both of them now corrected the second one correctly as a blue. Let's go to the next one. So now here's a red. Being below the line, both of them predicted as red, and so both are correct. Red predictions actually predicted red. The next. Well, so here's another blue that's above the line, which is correctly predicted as blue by both of them. The next, another blue that's correctly predicted. And as you can see, the accuracy updates with each successive prediction. The next one. Oh, this one came close. So this is the red, and reds are below the line. So it's clearly, comfortably below the flexible curve, but it's just barely below the straight line, but just barely counts. It's classification, so that counts as a correct prediction of red, even by the straight line. There's another red prediction that's correctly predicted by both of them. And another red prediction that's correctly predicted by both of them. You can see that both of them are doing fairly well so far. Then here's a blue prediction, correctly predicted by both. Another red that just barely makes it under the straight line, very comfortably under the flexible curve, but counts as a red for both. Then a blue that's correctly predicted by both above the line. Then another red correctly predicted by both below the line. Another red correctly predicted by both. Whoa, okay. Now this one gets interesting. Because remember, red dots should be below the line. So the straight line predicted that that's a red. So that's correct. But anything above the line, so this flexible curve predicts that that should be a blue, but it's a red. So that's an incorrect prediction. So a second incorrect one by the flexible curve right there. Well, there's a blue that's predicted correctly by both above the line. And here's a blue, which is below the line for both. So both of them get this wrong. For both of them, you have one actual blue that's predicted as red. So both got that one wrong. Here's a blue correctly predicted by both above the line. Okay, and here's another one in between. So as a blue, above the line, this is below the flexible curve. So that means that the flexible curve predicted that as a red, but actually it's a blue. So that's another error for the flexible curve. But for the straight line, it was correctly predicted as blue above the line. And then there's another correct prediction for both. And then the last, a blue that's above the line for both. So that's, we're just simulating 20 at a time. And so we have for next month, with 20 simulations, the flexible curve only got 80% accuracy and a straight line only 90%. Well, 90%, which is better than 80%. And so even though the flexible curve did perfectly on the original data, on the subsequent data, the straight line actually did better. So I went ahead and redid this simulation of 20 random dots a number of times. This one on the left is what we just saw with a random simulation of 20 dots and with the accuracy of flexible curve and a straight line. And the same, every time, exactly the same two curves. The second simulation the flexible curve did really badly with only 65% accuracy, and the straight line only a little bit better with 85% accuracy. So there's a lot of exceptions in dots, but still the straight line did significantly better than the flexible curve. And a third simulation, the straight line got everything perfectly correct with all the blues and reds correctly classified, but the flexible curve did only 75% that time. So I went ahead and did this 5 times. So 5 times representing 5 future months, and these are the results. So what we can see here is that for the flexible curve, you got 80, 65, 75, 70, and 65% accuracy, even though the original data set was 100%. The average accuracy for future data was 71%. The straight line, on the other hand, starting with 80% accuracy on the original data set, got 90%, 85, 100, 185% accuracy for an average of 92% accuracy on the future data. And again, this is on completely random data that was simulated. So we can see that the flexible curve consistently did significantly worse in future data than in the original data. This is clear evidence of overfitting, meaning that 100% that you saw, if that's all you looked at and thought that's a performance of flexible curve, well, it was overfit because it really was not that good. Now, the straight line, on the other hand, performed quite well in future data sets. The fact that it got 80% on the original, which didn't seem that good, but in future data sets, it actually got 92%. That means that 80% was not an exaggeration. It was actually an understatement in this case. That means there's no overfitting on the part of the straight line. I will note, though, that it is highly unusual that in future data sets you actually get accuracy that is better than the original one. And that's just a random effect, the fact that I'm only doing 20 variables at a time, and just for the randomness of it. Almost always, even when there's no overfitting, the future data sets will perform slightly less than for the original data. And if it's only slightly less, we consider there's no overfitting. But when you see such a huge difference from the original performance to the future performance, well, that there is clear evidence of overfitting. So the issue here of what we consider overfitting is looking at fitting current data versus predicting future data. And this is a fundamental paradox you have with models of predictive analytics. The fact is that we want the model to fit the past data that we have that we're using for analytics as well as possible, but we want it to also fit the future data that is coming up. And unfortunately, you can't eat your cake and have it too. You can't perfectly fit past data and perfectly fit future data. This is a great paradox. The fact is that the more perfectly a model fits the past data, then the more it loses sight of its ability to fit the future data as not yet seen, and that is, it loses the future predictive power. And this is what is called overfitting. When the model fits the data you've given it, which is past data, so well that it actually does poorly on the future data. One example that I like to give to understand this is that if a professor gives a practice exam to students to prepare for a final exam. Now, the wrong way to study with a practice exam is, and a lot of students unfortunately do this, they take a practice exam, they read the questions, read the answers, and they use that to study. And then they take the practice exam without looking. Well, a student might do that and might get 95% on the practice exam. But then when the real exam comes up, they might do really poorly. Maybe they'll only get 60% or only less because they basically memorize the practice exam and were not able to prepare for the future exam. A proper way to study would be to first study, do their best studying, and then take the practice exam, and maybe they'll only get 50% on the practice exam that first time they tried. But then they study some more and learn some more. And when they get the real final exam, maybe they get 80%. And that's similar to what you have in machine learning. So what's going on is that in any data set, there are systematic patterns going on, and there's some random noise. The systematic patterns are the physical laws or the social science laws of what is actually going on in nature or even in the social environment. And these are systematic, stable, ongoing patterns. However, real life is also random. There's just some things that are unpredictable that happen that mess up with the systematic patterns. So all data sets have these key aspects. The goal of predictive analytics is to find the systematic patterns, because the idea is that the systematic patterns you have from the past will continue into the future. And by finding the systematic patterns, the models will be able to detect what happens systematically in the future. Unfortunately, overfitting mixes up the systematic patterns and the random noise. So in this data set, as I said earlier, the systematic patterns is that the blue dots tend towards the top left and the red dots tend towards the bottom right, but there's some randomness. Overfitting means that the model mixes up both. It captured the general systematic pattern. You can see it generally trends to put the ones on the top left up and the ones on bottom right down. So it captured that, but it mixed it up with some random noise by doing this curvy thing over here, which is just totally random. And this model captured a mixture of systematic and random. In contrast, a good model like this straight line in this case, it's a simple case, but it demonstrates a point, only captured the systematic pattern. The top left, blue, bottom right, red. And it just ignored the noise, and it made some errors. It will make some errors when it ignores noise. But over time, this capture of systematic patterns and ignoring the noise tends to be more accurate than one that captures the noise from the very beginning. So that's the general idea of what we look at when we talk about overfitting. So this video, unfortunately, does not talk about how to resolve overfitting. That will be covered in another video. But hopefully you understand now what's going on, what is underlying the data set and how models try to fit them and might try too hard and overfit versus models that just try to get the systematic patterns and not overfit.